We will work on chapter 3 in class exercise 1, and that is there are two problems here, 1 and 2. We will work on one of the problems. The other problem you can solve using the same strategy and look at the solution that is being provided to you. Let's start with first problem about drawing a free body diagram. So for this given system, let's draw a free body diagram for hook A and indicate all the forces with appropriate direction and angles acting at hook A. So for free body diagram, we isolate the hook from its surrounding. That's step number 1. And we set up the coordinate system at that point, which is x-axis going right positive, y-axis going up positive, and then we indicate the different forces that are applied to hook A. So this point is our hook A. There is one force applied to hook A, which is 600 Newton. Another force, this is one. Second force is force in cable AB. You can call this tension force TAB going away from the hook. Remember, tension always goes away from the hook. And the third one is this force, which is going in cable A to C. That's because of the spring. So we can say that this force FAC is same as the spring force. Okay, and that completes the free body diagram. We also need to indicate the directions. So this is 3, 4, and 5. So this information is useful when we project this force along x and y axis. And for tension AB, we know this angle, which is 30 degrees. Okay, so that's the free body diagram. This is actually in class exercise 1, question number 1 from your handout. Now, the second problem from in class exercise is more involved, because in this problem we will actually we will draw free body diagram and we will apply equations of equilibrium to solve for unknowns. Determine the tension in cables AB, BC, and CD necessary to support 10 kg and 15 kg traffic lights at B and C respectively. So I'm just writing the weights of traffic lights here. So this is 10 kg at B and C it's 15 kg. Also find the angle theta. So this is one of the unknowns. So we need to determine tension force in cable AB, BC, and CD plus this angle. So we need to solve for 4 unknowns. And we have only 2 equations of equilibrium. That means we need to, for one free body diagram, that means we need to draw 2 free body diagrams. And the key points of interest are point B. So we can draw free body diagram for point B as well as C. Now, if we start with C as our free body diagram, then number of unknowns are we do not know force in cable BC, so that's 1. We do not know force in cable CD, that's unknown number 2, and we do not know the angle theta, which is unknown number 3. But we can solve only up to 2 unknowns with one free body diagram in 2-dimension problem. So this is not going to help us. So that's not a good idea. How about drawing free body diagram for B? So then we have one unknown, which is force in cable AB, and the second unknown is force in cable BC. And because we have only 2 unknowns, we are able to solve it. So let's start with that. Draw free body diagram for B and indicate all the forces that are being applied. You can pause the video, try to draw it yourself, and then compare your answer with my answer by unpausing it. Okay. Free body diagram, FBD is the short form for free body diagram. So FBD at B, this is point B, that's x-axis, this is y-axis, and this is B. Now forces, there is force here which is FBC in the horizontal cable. There is force acting down because of the weight of the light, which is 10 multiplied by 9.81 newtons. Remember, 10 is mass, kilogram, but force has unit Newton, so we need to multiply this with gravitational attraction, so gravitational acceleration. And this is force in cable AB. And we know this angle, 15 degrees. Okay, so that's our free body diagram. And now we need to apply scalar solution and solve for unknowns, and the unknowns here are force in cable AB and force in cable BC. So we have two unknowns. So apply these equations of equilibrium at B, sum of forces in x direction, and we assume that if the force is acting right, then it's positive. If it's acting left, then it's negative, equal to 0. FBC is acting right, so FBC is positive, but FAB and its horizontal component FAB cosine 15. So we need to take the cosine of this angle and project FAB in this direction. And that is negative, so it is 0, and that's equation number 1. Second, sum of forces in y direction equal to 0, and we assume force acting up is positive, and FAB has vertical component sine 15 minus we have the weight force, which is this force 98.1 newtons, equal to 0. That's equation number 2. So we have two equations and two unknowns. So solving 1 and 2, we get FAB equals 379.02 newtons, and we get FBC as 366.14 newtons. So we have solved for two unknown forces, FAB and FBC, using free body diagram at B. Now it's time to draw free body diagram for C. However, for C, now we already know the force in FBC acting at C. Now cable only supports the tension load, so at C it's the same tension load as this force, but we will draw the arrow in the opposite direction when we draw free body diagram for joint C. So for C, force in FBC is no longer unknown. We already know the value of that, which is 366.14 newtons. So let's draw free body diagram for FBD at C. X, Y coordinate system, and the forces are FBC. This angle theta is unknown. Force in cable BC, it's the same force but in the opposite direction for C. This is point C. So we set up our coordinate system at that point and draw free body diagram. And this is the weight of the light at C, which is 15 times 9.81 newtons. So equations of equilibrium at C. Sum of the forces in x direction equals 0. Going right is positive. So we have FBC, which is going left, and we have horizontal component of this is FCD, and that's positive. So this is minus FBC plus FCD cosine theta equals 0. See, we do not know the value of theta, so we will leave this as is. Sum of forces in y direction, positive going up, is equal to 0. This is second equation of equilibrium, and FCD sine theta minus weight of the light, which is this, equal to 0. That's number 2. Now for this equation number 1, we know the value of FBC, so we can say this is minus 366.14 plus FCD cosine theta equal to 0. And that's still equation number 1. So to solve equation 1 and 2, we can, by solving equation 1 and 2, we can solve for FCD as well as theta. And easy way to solve these equations is to write these equations, rearrange this equation as FCD sine theta equals to 147.15. So I have just moved the 147 on the other side of the equal to sign. And from this equation, we can say that FCD cosine theta equal to 366.14. And what we do is now we divide this rearrange equations, equation 2 by equation 1. So FCD and FCD will get cancelled, and sine theta divided by cosine theta is tan theta, and this number 147 divided by 366 is 0.401, and then we can calculate angle theta using tan inverse of that number, and that is 21.89 degrees. And once we know angle theta, we can substitute this angle theta into either equation 1 or equation 2 and calculate FCD. So FCD calculated from that is 394.68 newtons. So we have solved for all the unknowns. Forces in 3 cables, AB, BC, and CD, and angle theta. The next problem from in-class exercise is this spring problem, which is very similar to the traffic light problem, where this shaded spring indicates the original position of this system, where the weights are not attached. And when these weights are attached, the spring stretches, and whatever we see here, that's the final position of the spring. Now, depending on how much deformation we got on the spring, we need to calculate the values of these cylinders, or the masses of these two cylinders. The system is symmetric about vertical axis going through center. So what we can do is we can draw free body diagram only for hook A and calculate the weight of mass of the cylinder, and the second cylinder has the same mass. So I recommend that you try to solve this problem yourself and then compare your solution with the solution that is being provided to you. Thank you.